SwayamPrabha. Digital India. Educated India.
Today we look into stress strain behavior of shape memory alloys at various temperatures, at low temperature and at high temperature. So, we will start with low temperature behavior. Now, again we are familiar with this diagram, the characteristic temperatures for shape memory alloys vary with stresses, yes, and this is MF, MS, AS and AF, and we know that in this region we are martensite, in this region it is austenite. So, here by low temperature behavior means when the temperature is below the martensite finish region, which means we will start from here. So, at this region at 0 stress and when the temperature is below martensite, the material is in twinned martensite phase. So, we will start from here, we will load it and then we will unload it and then we will see how the material behaves. So, below this we will draw the stress strain diagram. So, this is stress and this is strain. So, as we keep loading the material, the stress strain diagram initially looks like this. Initially it is linear elastic. So, it is linear elastic because if you unload it, it comes back to where it started. Now, as we know that after some value of stress, the material starts transforming to detwin martensite. So, here the slope of the material becomes very bare minimum, it is quite low, and after the slipping ends, the detwin martensite again shows some elastic behavior, and then after that slipping takes place and again we see a plastic behavior. So, if we call this as our zone 1, so in zone 1 we have linear elastic behavior, and this is in the twin state, and this entire study is being done below MF, and that is what we mean by low temperature. Then we can call this as zone 2. So, this we can call zone 2. So, zone 2 plastic behavior, this is because of detwinning. So, the twinned martensite starts detwinning. So, the detwinning starts here and and the detwinning finish here. So, we can see that this is sigma critical start, this is sigma critical finish. So, this is the stress at which detwinning starts, this is the stress at which detwinning ends. Now, if we load it beyond this, then the detwin martensite shows a linear stress strain behavior. So, again linear behavior after detwinning. And slope same as 1. So, slope here and here are almost same. Now, this shows a linear behavior up to some range, then beyond this the material starts slipping and the behavior is again plastic. So, we can call this as zone 4. And plastic deformation due to slip. Again we started from here, the material was initially linearly elastic, which is this, then after some time the material process sigma CRS and sigma CRS and till sigma CRF, the detwinning takes place and within this the slope is very less. After that it is already detwinned and the behavior is linearly elastic, and then beyond some stress slipping takes place. So, we can call it sigma CR with SL. SL starts for slipping. So, beyond this slipping takes place and that is what is shown here. Now, we will see if we start unloading at various points how the material behaves, or if we vary the temperature at various phases how the behavior looks like. So, now we will draw another diagram, and in this diagram apart from stress and strain we will have temperature as well. So, we have stress here, we have strain here and we have temperature here, and along this line the stress is 0. So, we have martensite finish, martensite start, austenite start and austenite finish. Now, when the temperature is below MF, we have the low temperature stress strain behavior that we drew just now, same diagram. Now, say we are increasing the stress and then we have point A here and we have point B here. So, point A slipping, not slipping, it is detwinning. At point A detwinning starts, at point B detwinning ends. Now, before detwinning, when the material is linear, if we unload it, it follows the same path and it becomes 0. In between A and B, when the detwinning takes place, suppose here if we unload it, then it follows this path. It does not come to the 0 strain, rather it unloads, rather it goes down from here, and a permanent deformation remains here. Now, again this deformation is not permanent. If we heat it up, the material becomes austenite and the deformation becomes 0. Till B we get the same behavior, because till B the slipping takes place. At B also, if we unload it, it unloads in the same fashion. Now, from here, if we suppose increase the temperature, the material is martensite. So, till AS it remains like this. After AS the transformation takes place and the material becomes austenite. Once it becomes austenite, it regains its original shape due to the shape memory effect. Same thing happens here. So, here it was fully detwined, here it was partially detwined. On being unloaded, some amount of strain remained, and then on being heated, it transformed to austenite and it regained its original shape. Now, suppose if I load it further, it goes till a point C, and point C is a point where slipping starts taking place. So, on set of slipping in between B and C, as we saw that it is linear and the slope is same. So, slope between O and A and slope between B and C is same. So, here in between B and C, if at any point if I unload, it follows the same path and it comes back here. Now, this amount of stress, this amount of strain, let us call it epsilon p. So, the epsilon p is the strain which is the maximum strain which can be recovered. So, epsilon p maximum strain that can be recovered. Now, after slipping, if we keep loading it, after some time the material fails. Now, if we unload it from here before failing, it takes this route, and then it is if I increase the temperature, it does not come back totally here. So, if I increase the temperature, after AS some transformation takes place, but it does not go back to where it started. So, if I show it by a different color, so it goes back to somewhere here. Now, this is the amount of strain that is shown here that cannot be recovered, and let us call that as maybe epsilon pu. So, epsilon pu cannot be recovered fully. So, if we load it beyond slipping, then on unloading and even after heating we cannot recover the entire strain. So, some amount of permanent deformation remains in the material, and maybe we can call this as O dash. So, O dash the strain that remains, remaining strain, unrecovered strain. Now, let us imagine that we are at B, after loading we are at B. Now, from B, instead of unloading, let us say that we are increasing the temperature of the material. So, again if we draw the previous diagram showing stress temperature, this is what it is. Now, when we are at B, that means we are somewhere here, initially the temperature is below MF and the material has already detwined. So, stress is relatively higher. Now, from here the material is fully martensite. So, if I look at the xi versus T diagram at this level, it would look like this. So, this is our xi versus T diagram. So, xi versus T at sigma corresponding to B. Here, from here if we start increasing the temperature, it takes this route, which means the xi follows this path. Initially xi was 1 because it was martensite, and then it follows this. So, the temperature increases. Once it is in this region, the temperature increases and our xi decreases, and once it crosses this here, it becomes 0. So, it becomes fully austenite. So, starting from B, if I increase the temperature, the material becomes austenite, and once the material becomes austenite, its elastic modulus increases. Austenite phase has higher elastic modulus than the martensite phase. So, the slope of the stress strain diagram here increases. So, the strain value changes because the stress remains same, but the Young modulus increases. So, the stress reduces. Now, from here, if I again reduce my temperature, it will follow this path and it will become martensite. So, again it will become stress induced martensite, and it will get the same strain which it had before. Now, once the material is austenite, if I unload it, so now from here, so initially we started from here, we followed this path. Now, suppose if I want to go toward this side by unloading, then the material will still remain austenite. So, no more change to take place. However, instead of doing that, so remains austenite. However, if I reverse the temperature from here as we discussed, then the material becomes again stress induced martensite, and the stress remains at strain remains stress strain, I mean stress this point B again is achieved. So, the stress and corresponding strain remains of this amount. Now, from here, once it has become stress induced martensite, I can unload it, and if I unload it, it will again follow the same path and it will show some amount of remaining strain like it is shown here epsilon p, and then on hitting from here. So, if I unload it from here, it will come back here, and then by hitting I can go here and the material becomes again undeformed. So, we can take different paths from a certain position in this diagram, and accordingly the material behavior will change. We could directly unload and then heat it up, we can heat it up and again cool it down and unload, and accordingly as per these two diagrams the material behavior will change. Next we will talk about now we will talk about pseudo elasticity. Now, pseudo elasticity, to understand, again we have this diagram, and we have MF, MS, AS, AF. Now, here instead of having a low temperature stress strain behavior, we will look at high temperature stress strain behavior. So, at temperature which is beyond epsilon f, and also it should be less than MD, so that stress induced martensite can take place. As we saw in the last lecture that if you cross a temperature called MD, then stress induced martensite transformation is cannot take place, because before that before we achieve the required stress, the critical stress corresponding to slipping is achieved and the material slips. So, we have to be within MD and AF for to observe the pseudo elastic behavior. So, what happens here is once we start from here, and if we keep increasing the stress, then as the material crosses these lines MS and MF, the transformation takes place. So, initially the material is austenite. So, it has a linear stress strain behavior. So, as we keep increasing the strain, initially it is austenite. So, it shows a linear stress strain behavior. Once it crosses these lines, then the material starts becoming stress induced martensite, and then the slope of the stress strain curve changes and it becomes very close to 0, and then from there if we unload it, then initially the relation is linear, and after that while unloading, once it crosses these regions in the downward direction, the austenite transformation takes place and it is recovered quickly. So, that is how the diagram looks like. So, this is when our temperature is between austenite finish temperature and and MD. Now, suppose we are starting at a temperature here between AS and AF. In that case also initially and also assume that initially the material is austenite. So, in that case also the initial part of the stress strain diagram is same, because initially it is austenite, then the martensite transformation takes place once the stress crosses this MS and MF lines, and then it shows a behavior like this, reduced slope, and on unloading initially the behavior is like this, same thing, but at the end it comes back to where it started. So, here. So, while unloading, when it crosses these lines AS and MF, the martensite from martensite to austenite transformation takes place, but because the temperature is less than AF, so the full transformation does not take place. So, some part of the strain is yet to be recovered. So, the behavior here looks like this. So, full recovery is not possible here, and this is when the initial temperature is between AS and AF. Now, this phenomena is called pseudo elasticity and it is known as super elasticity also. So, here we can see that in the stress strain diagram there is a hysteresis. So, it is associated with dissipation of energy. So, that is why it is but and again it is elastic because it is coming back to where it started. So, this is it makes it ideal for use as damper or any energy dissipation applications. Now, we will talk about a two-way shape memory effect. So far we have seen that our shape memory effect is like this. We have a material in undeformed shape, it looks something like this, and then in the deformed shape it becomes like this, and then on heating it regains the shape. But in case of two-way shape memory effect, it may not the material may not show a full recovery, it may show a partial recovery like this. So, this is deformation, this is heating. Here the material is in the martensite phase, deformation is again in the martensite phase, we are heating it. So, it is beyond austenite, but here its full recovery is not happening, and then on cooling, the interesting thing is that on cooling it can again get its bent shape. So, previously when we are talking about one way shape memory effect, after that by cooling we were not getting this shape back, it was remaining in the undeformed shape, but in a two-way shape memory effect by cooling and heating the material can switch between these two shapes, and so this is T less than MF. So, it is a two-way actuation. Once the material is here, if I cool it, it gets the bent shape, if I heat it up, it gets this shape which is not fully undeformed shape, but it is very close to the undeformed shape. So, that is a two-way shape memory effect. Now, to impart the two-way shape memory in the material, there is a process called training. So, through training the material is made to behave like a two-way shape memory effect, and there are different methods of training. So, mostly it involves some kind of thermomechanical cycle. The material is gone through a thermal cycle or a mechanical cycle or a combination of both, and that imparts two-way shape memory in the material. And there are different techniques for doing this training. They can be over deformation, there can be repeated cycling which is SME. So, repeated cycling of shape memory effect means stress, it is not stressed, only the temperature is varied and the shape memory effect is seen, and it is repeated few times, and there is repeated cycling which can be pseudo elastic. Again, pseudo elastic means our temperature is constant, we are cycling the stress, and the pseudo elastic behavior is observed, and that is cycled quite a few times. And there can be combined ASME and pseudo elastic cycling, and there can be constant temperature cycling. So, these are the various techniques by which the shape memory alloy is trained to show two-way shape memory effect. Now, these methods are described in more details in the book by Chopra and Sirohi. So, if you are interested, you can refer to the book and learn more about these training techniques. So, this was about today's lecture. We have seen the stress strain behavior in low temperature and high temperature, at low temperature and at high temperature, and we have seen that at high temperature, if we cycle the stress strain, it shows pseudo elastic effect. Now, gradually we will move on to the constitutive modeling of these materials. So, with this, let me conclude this lecture here. Thank you.